Okay, hi everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So let me see what interesting questions there are that have accumulated. I think we have some left over from last time. Maybe we'll start with those. Okay, I see one here from Jack. Why is there a size limit for planetary bodies in the universe? Is the size of Jupiter the largest that is possible? Okay, so interesting question. So things the size of the sun become stars. Things the size of Jupiter stay as planets. What makes that difference? And does it always have to be that way? What is a star? A star is something that has lots of nuclear reactions going on. What's happening inside the sun, for example, is that there's enough, the things are being sort of pulled together enough that, for example, hydrogen atoms that actually they're just the protons, the nuclei of hydrogen atoms are being kind of pulled together hard enough that the protons can merge and release a lot of energy through a nuclear reaction. So normally, two protons, they both have charge +1. The sort of rule for electricity is like charges repel. So that means protons are being pushed apart by electrical forces. In order to get the protons to actually crash into each other, you need to give them lots of energy so that they can overcome the force of repulsion associated with their electrical charges. Well, in something like the sun, the sun is hot enough that those, for example, the center of the sun is about 10 million degrees centigrade. It's hot enough that what temperature means is that tells you the average energy of each of the individual particles. And so at 10 million degrees, you're absolutely hot enough that two protons can be going fast enough that they overcome that energy barrier associated with electrical repulsion and they crash into each other. What happens when they crash into each other? Well, then the strong nuclear force takes over, the force that will bind nuclei together, the force that causes one to be able to have lots of protons and neutrons bound together in the nuclei of heavier elements. That force takes over when you get within, 10 to the minus 15 meters roughly. Let's see, what is that? A millionth, billionth of a meter. When you get to that distance, which is about the size of a proton, when things like protons get that close together, there's a very strong force of attraction between them, which will bind them together. And that's how we come to have atomic nuclei from helium, lithium, beryllium, boron, and so on down the periodic table that have many protons in them, even though the protons are repelling each other through electrical forces. They're being pulled together by the strong nuclear force. So what's happening is something like the sun is that protons mostly are being made to go fast enough that they overcome the repulsion associated with electrical forces. They can kind of, collide together. The strong nuclear force takes over. What does that strong nuclear force lead to? It causes those protons to be combined into something which might eventually turn into a helium nucleus, for example. And it turns out that when they bind together, they release energy. And that's the energy of nuclear fusion. And that's the energy that powers the sun and powers all stars. And so essentially, when you have things like protons that are able to be sort of pushed together hard enough, they will undergo nuclear fusion. The nuclear fusion will generate lots of energy. And that's what makes a star go. Now, it's a little bit complicated because there are a couple of different things going on. So one question is, how do the protons get sort of pushed together enough that they undergo nuclear fusion in the first place? Well, the main force that does that is the force of gravity. That's the force that is kind of making that sort of pulling the pieces of the star together. Now, what happens is that once the things are sort of squashed together enough that nuclear fusion can occur, then they start generating energy, then the temperature goes up, then the things start going fast, and that allows fusion to happen in different ways. So let me try and unpack that. it's a little bit complicated. So one way that the primary thing is, can you get protons to collide and undergo nuclear fusion? So one way to do that might be you just take all those protons and you put them in a big box and you just squash the box and you just put huge amounts of pressure on this box and just push these protons together. That will be one way to get the protons to get so close that they can undergo nuclear fusion. That's sort of way number one. Way number two is you don't do that, but you just have these protons running around fast enough that two of them just randomly, if they're on a collision course for each other, they will not deflect as a result of electrical forces. They'll just successfully collide. And if they're going with enough momentum, that will happen. So there's two different ways in which you can kind of get those protons to be sort of squashed together to the point where nuclear fusion can happen. So once you have a star going, the star is producing nuclear fusion. That's producing energy. That's making the protons and other things in the star have high energy. That's causing them to be able to, just by virtue of their energy, their kinetic energy, to be able to overcome this potential barrier associated with electrical repulsion and undergo nuclear fusion. That's one mechanism for having that happen. The other mechanism is just that you're squashing things together. So what basically happens when stars form is matter starts getting pulled in by the force of gravity, and at some point it gets pulled in hard enough that essentially protons end up starting to collide together, get close enough that nuclear forces can start working. And then at that point, as soon as nuclear forces start working, the thing essentially lights up and becomes a star, because you've squashed enough protons together that they can produce energy, that enough fusion is happening, you produce energy, you heat the thing up, the thing becomes a star. So first of all, there's sort of compression through gravitational forces, then the thing kind of heats up and you're able to get more fusion happening just by virtue of the energy of all the particles running around inside the star. So the question is, at what size of object is there a kind of enough squashing due to gravity that you can get it to kind of undergo nuclear fusion and kind of light up like that? And the answer is it's somewhere between the size of Jupiter and the size of the sun. The sun is actually a comparatively large star. There are stars much, much larger than the sun, both stars larger in terms of their mass and much larger in terms of their size. For example, a star like Betelgeuse is a red giant star. It's a comparatively cold star, but its size is, in our solar system, it would reach about out to the orbit of Jupiter. So it's a huge star. It's a rather diffuse star. It doesn't have a particularly high mass. It's larger than the sun, but not outrageously so. But the sun is, in the spectrum of stars, is a comparatively, it's a decently large star. There are stars that are a tenth of its mass, maybe less than that. As you go down, I'm not exactly sure what the cutoff is. Maybe, I don't know, maybe 5% the mass of the sun, something like that, maybe a little bit more than that, at which below that mass, you just end up with things like Jupiter, planet-like things. You do not get enough force of gravity to start nuclear fusion to start the thing behaving like a star. And the thing, it's again a little bit complicated because the extent to which nuclear fusion can happen and exactly what all the barriers to nuclear fusion are and so on depend on what elements exist in the star. So for example, in the sun, the primary thing that is burning in the sun is hydrogen, turning into helium. But as the star gets older, it might have used up most of its hydrogen. It will have turned it into heavier elements, and then those will have to be combined together. And among other things, the electrical repulsion of a heavier nucleus with more protons in it is larger than the electrical repulsion for hydrogen. So different things happen. When a star has a supernova, what's happening is that the star is kind of there's a force of gravity that's causing the star to be pulled in, and there's a force that's associated with the temperature of the components of the star that's sort of pushing the star out. And what ends up happening in a supernova is that the force pushing the star out can no longer, you've kind of burnt it through enough of the fuel, in effect, that the force pushing the star out can no longer overcome the force of gravity. The thing contracts. It does so rather rapidly. As it contracts, new kinds of nuclear fusion start up. So, for example, elements like silicon and oxygen, it starts to be the case. There's enough force of contraction that it can cause again, I'm kind of trying to simplify several things here, but basically can get to the point where those nuclei which have higher charge and sort of take more effort to cause to collide together, they can start colliding. When they start colliding, that releases a lot of energy, and that all happens rather suddenly. And so in a matter of seconds to minutes or something, the star will explode dramatically, and we'll see this, a supernova happens probably in our galaxy once every millennium, and it will light up the night sky for a few days and things like that. Last one that we know about that was visible from the Earth in a dramatic way happened in 1054 AD, and it left over the Crab Nebula. But so the answer to the original question about sort of Jupiter-sized things is yes, they'll stay as planet-like things. They will not light up as stars. There's a critical size at which the force of gravity will cause the thing to kind of compress itself, start nuclear fusion, and light up as a star. That critical size depends on the constituents, depends on whether it's mostly hydrogen or whether it has heavier elements in it. So you can have sort of a Jupiter-like thing that hasn't started off as a star, or one that has, depending on what constituents it has in it. And the question of how many sort of things that are sort of Jupiter-like objects are just sort of floating around the universe, it's not really clear what the answer to that is. It's not clear whether there's a distribution of star-like things that goes down to quite small sizes that just aren't lit up as stars, or whether there's sort of a cutoff to how big the things that are sort of independently floating around the galaxy might be. I mean, the other thing to realize is that solar systems, most stars, one didn't know that until fairly recently, but it's clear that most stars form planets when the stars form. The stars form as a sort of, they're pulled together by the force of gravity. They'll typically form an accretion disk. They'll form this disk around the star that is kind of a flattened area. The thing is rotating around. There's sort of this flattened amount of material, and that material will gradually clump together and will form planets. And for a star the size of the sun, we'd expect 10-ish planets to form from what we now know. And it's not clear what happens in the history of a solar system, what happens to those planets. How many planets that originally form are kept in stable orbits in the solar system, how many of them are ejected out of the solar system, how many might crash into each other, and so on. So, for example, in our solar system, the asteroid belt, mostly between the orbits of Mars and Jupiter, is a lot of sort of small things that probably came from the collision of planets early in the history of the solar system. And the question of how many lost planets there were from our solar system, we don't know the answer to that. We don't know even probably as comparatively recently as the time of the dinosaurs. We don't really know what other configuration of planets might have existed in our solar system. So it could be that our solar system had an extra 3 or 4 big planets, and they're off floating through space somewhere as things which are not big enough to make stars, but they exist as cold, solid objects floating through the galaxy. And we've seen fairly recently, it wasn't known whether there were interstellar asteroids, so to speak, whether there were things like asteroids that had escaped from another solar system and were sort of free floating in the galaxy. We now know that those do exist. One was observed, maybe 2 or 3 years ago now. Umanuma, I think was its name, if I pronounce it correctly. And you could kind of tell that it was an extrasolar asteroid because it when you trace its trajectory, you could see that it wasn't a trajectory that would cause it to actually successfully orbit the sun. It had to be something that wasn't in orbit around the sun, that was coming from elsewhere in the galaxy. And so that there's probably lots of rock-like stuff floating around the galaxy. One of the questions is it big enough that when it passes in front of a star, that it will make the light from the stars go down? That's one of the methods for detecting exoplanets, planets around other stars, is just seeing as the planet goes in front of that other star that you're observing, the amount of light coming from that other star will dip slightly. And if you see the light from the star repeatedly dipping, every 100 days or something, then a good explanation for that is, oh, there's a planet that's going around that star, and every 100 days it's blocking some of the light from that star. That's one of the methods for detecting exoplanets. And so one might think that something like that might happen for just random planets that are just sort of free floating through the galaxy. But it's much harder to detect that, because while you can kind of say, oh, well, my telescope might have drifted a bit, but I'm seeing a signal every 100 days, something happens precisely every 100 days. That's much easier to detect than just, oh, something went in front of my star. Was it something that went in front of the star, or was it some glitch? If it was a telescope on the surface of the Earth, was it some piece of cloud high in the atmosphere or something that got in front of the star? Only if it's this repeated thing is it easier to do the experiment to find out that it's really something associated with the star. Okay, there's a question here about from Jimmy about what happens to the electrons before fusion in the sun occurs. Okay, so here's the thing. When you have a hydrogen atom has a proton in its nucleus. Most hydrogen atoms have just one proton in the nucleus. The other isotopes of hydrogen, like deuterium, has a proton and a neutron in its nucleus. But basically, it's a proton in the nucleus, and there's an electron that's kind of going around the nucleus. It's kind of quantum mechanics says that this picture of it sort of just going around isn't quite right. But it's a very good way to think about it, is the electrons are sort of going around the nucleus. The thing to understand is the distance, the average distance that the electron is from the nucleus is 100,000 times the size of the nucleus. So in a sense, the nucleus is this little lump in the middle, and there's sort of emptiness out to the average distance that the electron is about 100,000 times the size of the nucleus, which in this case is just a single proton. So what causes the electron to kind of stay kind of hanging out with the proton? Well, it's a force of electrical attraction. The electron is negatively charged, the proton is positively charged. So the rule is, unlike charges attract. So there's a force of electrical attraction between those things. Okay, now as you put more energy into the atom by, for example, heating it, by heating it up, by having it bump into other atoms, things like that. As you put more energy in, what will happen roughly is that the electron will get just a little bit further away from the nucleus. And in quantum mechanics, it's a bit of a more complicated story, but the average distance that the electron is from the nucleus will increase slightly. Okay, well, there comes a point, very precisely, it's at 13.6 electron volts, where you put enough energy into the electron that actually that energy is enough to have it escape from the proton. So it's a little bit like the following. If you're on the Earth and you fire a rocket into space, you need the rocket to have a certain amount of energy. It turns out to be going at a certain speed. So if you want the rocket to escape from the Earth, it has to be going, in the case of the Earth, at 25,000 miles an hour. At that speed, the kinetic energy of the rocket will exceed the energy associated with the gravitational pull of the Earth. And it's the same kind of thing with an electron and a proton and a hydrogen atom. When the electron is given enough energy, it will escape from the proton. And so that process is called ionization. It will turn the hydrogen atom into a hydrogen ion, which is just a proton, and the electron will then be ripped out of the hydrogen atom, and it will be then free to do its own thing. So, for example, we commonly see when you have hydrogen gas, for example, that has been ionized. That's what we see. It's not necessarily hydrogen gas, it will be other gases. When you see fire, for example, that is an example of an ionized plasma in which atoms have been ionized, or at least partly ionized, in the sense that their electrons have been ripped out of the atom and are sort of freely floating around. So in the case of the sun, as the temperature increases, the electrons will be ripped out of their atoms, and they'll just be, the electrons are just freely floating around in the sun. And the thing that you might ask, what happens when the electrons collide? That's a much less that process primarily only involves electromagnetic interactions. There's no, when two electrons crash together, there is no known process by which the electrons can kind of merge into something like an atomic nucleus. There's no analog of the strong nuclear force that binds nuclei together. So you can have collections of protons and neutrons and so on. Those are so-called strongly interacting particles that can bind together into atomic nuclei. But for electrons, nothing like that happens. For electrons, the only force between electrons is an electrical force. There's actually other forces. There's a thing called the weak nuclear force, which also operates, that has to do with neutrinos and things as well. But there's no way to make kind of a sort of a nucleus made of electrons or something. There is, if you have an electron and a positron, positron is the antiparticle of the electron, you can make a little positronium atom that is about the size of a hydrogen atom, actually, that consists of an electron where instead of it having as its nucleus, so to speak, a proton, it has a positron, but that's not something that's tightly bound like an atomic nucleus. And so far as we know, that there simply isn't a way to have electrons interact strongly like that. Now, whether it will turn out to be the case, well, so the thing to understand is a proton has a very definite size. A proton is about 10 to the minus 15 meters across, a million billionth of a meter across. An electron, so far as we know, has no extent. It's just like a perfect geometrical point. Actually, we know only that it's smaller than about roughly a millionth the size of a proton. It's certainly smaller than a millionth the size of the proton. Now, in the fundamental theory of physics that we've been developing, electrons actually do have a definite size, but their size is probably around 10 to the minus 80 meters in our model. So it's absolutely tiny. It's a trillion trillionth the size of a proton or something. And if that's right, that's the correct size, then it would be the case that sufficiently high energy electrons, if sort of fired at each other, could have some force associated with them that is stronger than electromagnetic force. But you wouldn't see that until you were using so much energy. It's just unbelievably much more energy than we know any process to produce in the universe as it exists today. Okay, there's a question here. Boy, all kinds of physics questions here. All right. There's a question here from Brian. Why does it take a long time for a photon to go from the core of the sun to the surface of the sun, but only 8 minutes to reach the Earth? So I think it takes, Brian is saying 100,000 years. I thought it was a little bit longer even to go from the center of the sun to the surface of the sun. Okay, so here's how it works. If a photon is traveling through a vacuum, through empty space, it goes at the speed of light. And the speed of light goes roughly a billionth of a, it takes a billionth of a second to go 1 foot. It takes, needless to say, a year to go 1 light year. It takes about 8 minutes to go the distance from the sun to the Earth in a vacuum. So that's kind of the the fastest that a photon can go. Now, if you even have a photon in a piece of glass or water, what's happening is the photon is continually getting absorbed and re-emitted. So there'll be a piece of let's say, a water molecule, and the photon will get absorbed by atoms in the water molecule, and it'll get absorbed. It'll cause the electrons in those atoms to increase their energy, and the electrons will then decrease their energy again and emit a photon again. And there's a delay when that happens. So photon comes in, it's absorbed by an atom, then decays and re-emits the photon. But there's a slight delay. And that delay is what causes light to travel at a slower speed in something like water or glass. Light travels 1.33 times slower in water than it does in the vacuum. In air, it travels at very close to the speed it does in a vacuum. In glass, it's usually 1.5 times slower than a vacuum. In diamond, it's 2.7 times slower than a vacuum, and so on. And so what's happening in all these materials is the photon keeps on getting absorbed, re-emitted, absorbed, re-emitted. Every time there's an absorption re-emission event, the photon is kind of slowed down a bit. So in the case of the sun, what's happening is there are zillions of absorption re-emission events that are happening. And the effective refractive index, that's the measure of the ratio of the speed of the photon in the vacuum as compared to the material, that is effectively some very huge number. And so essentially a photon, you can think of the sun as actually being very opaque. The photon just sort of gets to something, and then it's being absorbed, re-emitted all the time, and that happens a zillion times in the passage of the photon from the center of the sun to the surface, and that's why it takes a long time. So let's see. Okay, there's a question here. Is there a way to reduce the energy of an electron so it falls into the nucleus? Okay, that was a question people were very keen to answer about 120 years ago. So the history of this was atoms had been sort of thought about in ancient Greek times as maybe that's what matter is made of, discrete atoms and so on, but people weren't very sure. By the mid 1800s, people were pretty sure that atoms existed. And there were two basic lines of evidence. One was when you do chemistry, there are all these ways in which you get exactly twice this amount of material as compared to that. And you can explain these numbers, these ratios, if things are made of discrete atoms. That's one line of development. The other one was processes like Brownian motion. So Brownian motion was first observed by a chap called Brown, needless to say. It was a little pollen grain in some water, for example, and you could see through a microscope the pollen grain was kicked, discretely kicked, moved around, and those little kicks were water molecules hitting the pollen grain and moving it. And that process of sort of discrete kicks kind of told you there were discrete things that made up the water rather than it being just this continuous fluid. Right now, people know that matter is made of discrete things, namely atoms. There's sort of been a big question of whether space is similarly made of discrete things. I think our fundamental theory of physics that we've developed over the last year or so makes it pretty clear that space is also made of discrete stuff, although the size of those discrete atoms of space is unbelievably much smaller than the size of things like material atoms. It's probably, it's trillion time. I should be able to roll off my counts of trillions properly, but it's of that multiple trillions of times smaller than the size of atoms that we know about. So, okay, mid-1800s, people knew atoms existed. What were atoms made of? Well, a chap called Ernest Rutherford was the one who figured out that you could have particles, so-called alpha particles, actually helium nuclei, and you could fire them at an atom, and most of the time they would just go straight through. But just some small fraction of the time, they would be deflected through a large angle. So it's as if most of the time they just hit nothing in the atom, but just sometimes they hit some hard bit in the atom and they're deflected a lot. And that hard bit that they were hitting in the atom is the atomic nucleus. And what became clear is that the atomic nucleus had protons, and then much later neutrons got discovered, and it contains protons and neutrons. Then the electrons are sort of outside of the nucleus. Okay, so one of the first things that people wondered was, why don't electrons just lose energy and spiral into the nucleus? So, for example, in general, when things are sort of orbiting around through some force of, let's say things are being held in orbit by the force of gravity. So the thing is going round, and centrifugal force effectively is making the thing tend to try and get out of its orbit. Why does that happen? Well, if left to its own devices, something will just keep going in a uniform state of motion. So if you take something in space that has no forces acting on it, you throw it in some direction, it'll just keep going in that direction forever. So if it's going to be kept in orbit, you have to have some force that's pulling the thing, that's preventing it from just going in a straight line, that's causing it to go in, for example, a circular orbit. So for example, you might have a force of gravity that's doing that. That's how planets orbit the sun and things like this, moons orbit planets, etc. Okay, well, in order for the thing to keep going in its orbit, the planet has to have a certain amount of energy. If the energy is what keeps it sort of going around, if it didn't have that energy, the force of gravity would overtake it, and it will be pulled in to the wherever the gravity is coming from, the center of gravitational attraction, and the planet would just sort of lose energy and spiral in and crash into the sun. Okay, so the reason that doesn't happen, the reason that's not happening to the Earth, is the Earth doesn't really have a way to lose energy like that, at least not on a large scale. Now, in the case of when you have black holes, they're very small, a few kilometers across, perhaps less than a kilometer across, intense things with masses larger than the sun. Black holes can orbit very close to each other, and they do actually have a way to lose energy, and their way of losing energy is the emission of gravitational radiation. And so black holes, when they are orbiting around each other, they'll lose energy through gravitational radiation. That will cause them to spiral in, and the black holes will get closer and closer together. As they spiral in, they'll go faster and faster. They'll lose more energy through gravitational radiation, and eventually they'll lose enough energy that they just collide with each other. And that splat is a very dramatic event. And for example, we can now detect the gravitational radiation from black hole mergers that are happening pretty much all the way across the universe from us. For example, there are ones that we've seen that are from 7 billion years ago in the last year or two, which means that they're at least halfway across the universe from us. So it's a very dramatic event when two black holes finally sort of spiral in, having lost energy through gravitational radiation. Okay, so the question is, why does that not happen with electrons? When electrons in atoms in order to keep the electron in its orbit, so to speak, you have to have some force of attraction. That's an electrical force of attraction that will effectively accelerate the electron, because the electron, without any acceleration, will just keep going in a straight line. So you have to exert a force which causes acceleration of the electron. And one of the rules about electromagnetism is accelerated charges produce electromagnetic radiation. So for example, if you have the antenna in your cell phone, what's happening in that antenna is it's sort of more or less pieces of wire, and electrons are going back and forth inside those pieces of wire. And the acceleration associated with the electron going first one direction, then the other direction, and so on, that acceleration causes the electron to emit an electromagnetic wave, which is the radio wave, which is the thing that allows your cell phone to communicate with the outside world. So one of the rules about charged particles is accelerated charged particles radiate electromagnetic energy. Okay, so people knew that back in the early 1900s. And so they said, well, so why is it the case that electrons in atoms don't radiate electromagnetic energy, and spiral into the nucleus and go splat. Okay, so why doesn't that happen? Well, the answer was originally has an answer that was partly happened before quantum mechanics, but basically the answer is it's just a rule about physics that energy is quantized in the sense in the case of an atom, there are only a limited number of possible energy levels that the electron can occupy. So to say the electron is just sort of doing its happy thing, sort of going around the nucleus of a hydrogen atom, okay, all good, it has a certain energy. If you say that you kick it a bit, you can give it a higher energy and a higher energy. Eventually, the energy, you can get up to a high enough energy that it will escape from the atomic nucleus. But there are a discrete set of those energy levels. Actually, if you work it out in the theory of the hydrogen atom, the nth level has an energy about 1 over n squared. And so the levels sort of accumulate as you get up to this critical energy level, at which point you get ionization and the electron escapes from the atom. But so these energy levels are quantized. They're just a limited number of possible energy levels for the electron in the atom. So the way this is understood in quantum mechanics is basically a mathematical theory of why that happens. It doesn't really explain, quotes, why that happens. It's just a descriptive mathematical model for what's going on. And the sort of key idea that comes up in what's sometimes called wave mechanics, it's sometimes related to the Schrodinger equation, which is sort of a key equation in quantum mechanics, is roughly this. One thinks of the electron as being represented like a wave. And if you think about something like a piece of string, and you are sort of, let's say the string is like a violin string or something, and you're plucking the violin string, the string will have a certain mode that it will go into. So the string will be sort of, it'll bow outwards in some direction, and then it'll come back and down and keep vibrating in that way. That's one mode of the string. Another mode of the string is that it can go up and then down and then over like this. So in other words, it has sort of 2 humps in it, or it can have 3 humps. But if you fix the ends of the string to always be at a particular position, there's a fixed integer number of humps, a whole number of humps that the thing can have. So it can have just 1 hump, 2 humps, 3 humps, and so on. And those correspond when you're playing a musical instrument. When you kind of pluck a string, you'll find that there's both the fundamental frequency, that's kind of the 1 hump version, and then there'll be the overtones, the harmonics that correspond to these various different other numbers of humps effectively in the wave that's made by that string. So that's sort of the physical version in strings. The mathematics of the so-called wave function of electrons in hydrogen atoms works the same way. And the setup is mathematically very similar. And so what you end up finding is that there are just these discrete integer energy levels that are possible for the electron. And that's what quantum mechanics says. And so the reason the electron can't just spiral into the nucleus is, how's it going to get there? As it starts spiraling, it has to change its energy, but it can't change it continuously. It would have to change it in a jump. And it can't do that because the sort of gradual emission of radiation doesn't work. The only way it can emit radiation is in these jumps where it goes from one energy level to another energy level. And the way you see that in atoms, there are these so-called spectral lines. Different elements have characteristically different spectral lines. The spectral lines are associated with transitions from one energy level of electrons to others. And depending on the exact structure of the atom, you'll have different transitions that can occur. And that's what, for example, neon lights, the red of the neon is a particular energy level, a particular transition between 2 energy levels in the neon atom that causes that red light to be emitted. It's a particular frequency of photon that's emitted as a result of a particular transition in neon. Or for example, sodium lamps, there's a very particular, the sodium lamps are the D lines of sodium that emit this kind of orange light, and it's a very specific frequency of light that gets emitted because of a transition between 2 particular energy levels of electrons in sodium atoms. So the kind of descriptive reason why the electron can't just sort of spiral into the nucleus is because the energy levels of the electron are quantized, and so it can't just sort of gradually spiral in. Now, you might ask, how does that really work? What's really going on inside? And we're pretty close to being able to answer that question in our models. We don't, let me think for a second if there's a way to try to explain this. I think we're not quite there yet in terms of having a really simple explanation of quantization of energy in a hydrogen atom, but roughly, well, yeah, no. Come back in a couple of months. We might have a cleaner explanation by then. I think the story I would tell now has to do with these things called multi-way systems, which are kind of a representation of multiple possible histories for the atom, and the way that there's kind of interactions between those multiple possible histories and so on. Okay, there's a question here. Boy, we got a lot of physics today. Okay, there's a question just came in from Jimmy asking, how does one solve more than one electron systems? Well, boy, that's complicated. So the theory of the hydrogen atom in quantum mechanics was worked out in the 1920s originally, the basic theory. When you have just when you have a point atomic nucleus and you have an electron, then it's a pretty simple partial differential equation, and you solve for the so-called eigenmodes of that partial differential equation, you get the answer. It's all good. Okay, let's consider the helium atom. The helium atom has a point nucleus and it has 2 electrons in it. Nobody's ever found a nice mathematical formula solution for the helium atom. You can do a computer simulation of a helium atom using the Schrodinger equation, and that works really pretty well. But in terms of, is there a mathematical function that describes the helium atom? Well, no, not quite. So just to say how this works, people are familiar perhaps in mathematics with things like sines and cosines, exponentials and logarithms and so on. In mathematical physics, over the last 150 years, a couple of hundred years, there's a whole zoo of other kinds of so-called special functions of mathematical physics that people have invented. There's probably about maybe 200 of them that are in common use. And what's important about these functions is that they solve certain kinds of equations and they show up all over the place. Like they're things called Bessel functions. They were originally invented as a result of studying things to do with the motion of the moon. But they also show up in describing the shape of a drum head when a drum is, when you kind of beat a drum, and the way that it deforms and vibrates and so on. They also show up in a zillion other places. So these special functions have this feature that you invent them once and they show up in lots of places, and that's why they're useful. So in the case of the hydrogen atom can be solved. There's just a mathematical formula that describes this wave function for the hydrogen atom, and it's solved in terms of 2 kinds of special functions, things called Laguerre polynomials and things called spherical harmonics. And the Laguerre polynomials are just polynomials. My memory is not good enough to be able to recite the first few Laguerre polynomials. If you type them into Wolfram language or Mathematica, it'll be able to generate as many Laguerre polynomials as you could possibly want. But the Laguerre polynomials determine the radial. This wave function, it's a function of the position in the hydrogen atom, and you usually measure that by saying the distance from the center of the hydrogen atom as well as the angles around from the center. It's kind of like saying distance from the center of the Earth and then latitude and longitude on the surface of the Earth. So the radial function in the case of the hydrogen atom is Laguerre polynomials, and the functions that tell you about the surface, the angular functions, are these things called spherical harmonics. the spherical harmonics are kind of generalizations of sines and cosines. So sine and cosine represent kind of functions that describe in trigonometry, they describe sort of the x and y coordinates when you're just going around a circle and you specify what the angle is, and that tells you the x displacement and y displacement. Spherical harmonics is sort of a generalization of of sines and cosines to work on spheres rather than just on circles. And so the spherical harmonics are the things that determine the angular structure. And when you solve the hydrogen atom, you have these different energy levels. They were originally named, originally German names. A lot of this stuff was developed in Germany in the 1920s and so on. And so there's the s orbital and the p orbital, SPD, FG, I think is the sequence. There are these different so-called quantum numbers that determine the characteristics of which of those electron energy levels are you dealing with. So in the case of the hydrogen atom, there are 3 quantum numbers, usually called Lm and N, which determine the basic which energy level you're talking about in a hydrogen atom. Okay, that's the hydrogen atom. Let's talk about the helium atom. Unbelievably much more complicated. The whole story of the interaction between those 2 electrons and the possible wave functions that can occur with those 2 electrons, vastly more complicated. One of the things that's really complicated about it is this thing called the exclusion principle, that in its simple form just says things like electrons, kinds of particles like electrons, not particles like photons, but also particles like protons and so on. Electrons have the feature that in quantum mechanics, if you try and put 2 of them in kind of the same energy state, they won't let you do that. We actually think we know why that happens in the context of our models, and it has to do with essentially the failure to merge different possible histories of the universe in our multi-way graphs. But that would take a bit of explanation to say how that all works. But basically, this exclusion principle has constraints on the structure of the wave functions for the helium atom, and they're really complicated. So what happens, people have tried to make solutions for larger atoms, and gradually over the decades, one's been getting better and better at being able to reproduce the energy levels of even atoms like, I don't know, gold atoms or things like that. Gold has a 79, right? Is gold. Is it 80? 79. Which one? Gold and mercury are one apart. I forget. 79, I think. That's the number of, how embarrassing, I don't remember that. I do remember tungsten because its alternate name is wolfram. It's element 74, which means it has 74 protons in its nucleus. But anyway, if it has 74 protons in its nucleus, that means that when it's not in any way ionized, its sort of natural neutral state, it has 74 electrons. And the interaction between all those 74 electrons is unbelievably complicated. And it's been difficult to solve those equations. And it can only be done with some degree of approximation. And I'm not sure how accurately all the energy levels can be reproduced in something like a tungsten atom now. By the way, one of the things that's coming out of our models of fundamental physics is a new way to do those kinds of computations, which looks really promising. And I suspect that it will become possible to do sort of quantum mechanical calculations much more easily as a result of our models, actually making use of the fact that our models are fundamentally discrete. They have sort of atoms of space, just like computers fundamentally deal with discrete quantities. Now, the fact is that our atoms of space are unbelievably tiny, so there are huge numbers of atoms of space in our real experience of the universe and of space. But it turns out that by just using that sort of idea of atoms of space, you can make a scheme for computers to compute things, and they can get pretty good answers even when they don't have that many sort of atoms of space being used. So that's a new sort of method that we've been developing first for use in solving Einstein's equations for gravity, but it also looks very promising as a way of working out things in quantum mechanics. It's sort of a way of using the structure of our models to produce a more efficient way to compute how things work in the world. So it's possible that there will be changes in what can be done with many electron systems of heavier atoms. Gosh, let's see. I'm going to do a couple more physics things, and then we'll talk about something different here. Oh boy, there's a question from Attore. When an atom absorbs a photon and the same atom emits a photon, is it the same photon? Well, when you say 2 plus 2 and you get 4, no, 2 plus 3, you get 5. You subtract 2 again and you get a 3. Is it the same 3 or is it a different 3? The answer to that question is the same answer as the question about photons, really. Because essentially what's happening is that this photon is some, at least in our model of physics now, we have some real understanding of this, it's some configuration of these atoms of space, some connectivity of atoms of space. And that connectivity is destroyed when the photon is absorbed, and then it's recreated when the photon is emitted again. Now, is it the same one or is it a different one? I don't know. You know, it's like is it the same 3 or not? It doesn't really, I think, have a clear meaning. And so that's there isn't really that kind of identity. I mean, I think we are used to the idea that material objects maintain their identity because they're just sort of so many atoms in this material object that they don't sort of all transmute in some way at the same time. I mean, it's kind of in philosophy, there's this sort of old story of the ship of Theseus, where, you know, there's a ship, it's made from a bunch of planks of wood, and gradually the ship is renovated. One plank is changed, another plank is changed, another plank is changed. Eventually, all the planks have been changed. And then there's a question, is it still the same ship of Theseus, even though all the planks have been changed? That's kind of the same type of question as we're asking about electrons, or even more extremely about numbers in that arithmetic computation. Let's see, there's a question about from Van about the speed of light. Okay, it's about how is it an assumption that the one-way speed of light, how do we measure the speed of light given that we have to kind of sync up measurement instruments at the two ends of the speed of light? Well, let's see. I mean, the first way the speed of light was measured was very early, actually. It was measured in the 1600s. And it was measured by looking at the moons of Jupiter. And so how can you measure the speed of light from the moons of Jupiter? Here's how. So the moons of Jupiter were discovered in 1608 by Galileo. And what he noticed was that every few days, there are these spots of light that he identified as moons that are going around Jupiter. Okay, so you assume the moons of Jupiter are going around in a certain orbit. And you assume that, then you have to ask the question, when as the Earth goes around its orbit, the total distance to Jupiter changes. And so the question is, if you count the revolutions of those, let's see, how does this work? You're basically measuring the delay of that orbit as seen by the Earth when the Earth is on one side of its orbit and when the Earth is on the other side of its orbit. And so you're able to measure the speed of light by comparing how much different is the rise time, so to speak, of, let's say, Ganymede relative to what you would expect. Is the offset of the rise time of Ganymede, as it comes around Jupiter, how is that offset when the Earth is on one side of its orbit as compared to the other side of its orbit? So effectively, you're measuring the amount of time it takes for light to cross the distance that corresponds to the orbit of the Earth. So that's the first way that the speed of light was measured. Then within a fairly short amount of time, 50 years, maybe 100 years, an alternative method was used that involves a toothed wheel that was rotating very fast. And there was, the question was, you were looking at, I guess, interference of light with this toothed wheel, if I'm not mistaken. And that's a more direct kind of terrestrial way to measure the speed of light. But sort of conceptually, the way you measure the speed of light is you say you send a light pulse to somebody, and you have to, there's sort of all these kinds of ways to imagine that you have a sort of lattice of light pulses that allows you to define what you mean by synchronization. It's pretty arbitrary. I noticed, for instance, this Mars lander that just landed a few days ago, and people were like all, cheering on the Earth when the Mars lander landed. Well, were they cheering when the Mars lander landed, or what? Because the fact is, the speed of light is such that it probably took 20 minutes for the signal from the lander saying, I've landed, to get to the Earth. There's a 20-minute difference. There's a 20-minute time delay associated with light traveling. So the question is actually more extremely, if the spacecraft has a clock on it, and the question is, how is that clock synchronized? Is noon on the spacecraft synchronized to noon on the Earth or not? Well, noon on the Earth is 20 light minutes, let's say, and it's actually going to vary because the distance between Earth and Mars varies through the year, through multiple years, how is that going to be synchronized? It's sort of arbitrary how you do that synchronization, but it's perfectly possible to set up by having sort of a network of light signals being exchanged. It's perfectly possible to set up a consistent synchronization of objects, of events at different times. And when you know that those individual clocks are running at a certain speed, you can kind of use that to measure the speed of light. And the speed of light has been measured very accurately. In fact, okay, this is a little bit confusing. In the end, the speed of light is now in the system of units. The speed of light is actually locked to be a particular number. That happened a few years ago. And the reason it works that way is that length and time are related by the speed of light. And if you can define time you can define length in terms of the speed of light if you know what the time unit is, and you can define time in terms of this in terms of length if you know what the speed of light is. So the way the SI system, the standard international system of measurement works, the speed of light was actually locked at a particular value, and I guess it is which one is it that's standardized? Is it the second or the meter? I don't remember which one is the fundamental standard. It must be the second, because it's done in terms of the energy levels of the cesium atom. So that you've decided what the second is, and then you just use this fixed number to determine what the size of the meter is based on the speed of light. So it doesn't make sense anymore to talk about measuring the speed of light, because you'd just be changing the length of the standard meter, so to speak. That's you can ask questions about how the speed of light varies. The effective speed of light varies. It changes as you change the gravitational potential. So, for example, there's a thing called gravitational redshift, which happens. Let's not get into this. This is a whole different story. Let's see. Well, there's a question from Jonas here. What happens when you cool materials down? Fundamentally, the thing we have to explain is what is temperature, right? So materials are made of molecules, atoms, all bouncing around. The air, they're bouncing around in such a way that they keep on colliding with each other. They collide very frequently in the air, but they don't stick together. They're just bouncing off, and the temperature is determining the average energy of each molecule, and that determines how fast they're going. And with the parameters of air molecules, they don't sort of stick together. And as you decrease the temperature, what you're doing is decreasing the average energy of every air molecule, which decreases the average speed of the air molecules. And eventually, the air molecules are moving so sluggishly that when they can when they kind of hit, they will they'll be able to kind of stick together, and at that point the air will start to turn into a liquid. And in fact, that happens very suddenly at a very particular temperature. Air will turn into a liquid, just like water. You can go from steam, and at standard pressure at 100 degrees centigrade, steam will condense into liquid water. And what's happening there is as you lower the temperature, the average energy of the molecules is going down. That allows the molecules, which have forces of attraction between them, to kind of latch onto each other and kind of keep them kind of clumped together in a liquid. As you lower the temperature even further, in the case of water to 0 degrees centigrade, the molecules will be sort of able to, the forces of attraction will overcome the kind of energy that's associated with temperature, and the molecules will arrange themselves in a crystal lattice, for example, like in ice. So most materials have that feature, that as you cool them down, they go from gas to liquid to solid. There's usually different forms of the solid that can exist, different crystal structures at different temperatures and pressures and so on. But normally that's the sequence, from gas down to liquid, down to solid. Interesting question whether there can be more than one liquid phase, whether there can be more than one way of arranging the atoms and still have it correspond to a liquid. Looks like water may actually be a combination of two phases, which may explain some of the very, very bizarre features of water in which it differs from a lot of other kinds of liquids. But be that as it may, the basic sequence is gas to liquid to solid. Okay, so most materials, when you cool them down far enough, they'll eventually turn into solids. There's only one exception, which is helium. And when you cool down, let's say hydrogen, you cool it low enough temperature, it'll turn into a solid. You cool air down, it's a mixture of nitrogen and oxygen, the nitrogen and oxygen actually become liquids at slightly different temperatures. Minus 174 degrees centigrade, I think, is liquid nitrogen, if I remember correctly. So you keep cooling it down. Eventually, you get to solid, sort of solid nitrogen, and that's the end of the story. Now, as a question, is there a lowest possible temperature? Well, you might think if the temperature is the average energy of molecules, then sure, there must be a lowest temperature, because it's the temperature at which there is no average energy of molecules. Molecules just don't have any kinetic energy. They're just kind of sitting still, for example. And yes, there is a minimum temperature. It's so-called absolute zero, minus 273.16 degrees centigrade is absolute zero. That's the temperature at which, if you sort of extrapolated from the energies of molecules that we're used to, that's the temperature at which the molecules just have no energy. They have zero energy. They kind of would just be standing still. And so if there's any force of attraction between the molecules, that force of attraction will overcome anything else, and they'll turn into solids. Okay, that's the simple picture. There's one little glitch in that picture, which is, it turns out nothing ever gets to have actually zero energy. In quantum mechanics, there's a thing called zero-point energy, which is means that everything has these sort of quantized levels of energy, and that even you can't go below essentially half a quantized unit of energy. And that leads to this phenomenon of zero-point energy. In our models of physics, we kind of have an understanding of where zero-point energy comes from, and actually it's closely related to the way that space, the structure of space, is knitted together. If it wasn't for zero-point energy, if it wasn't for all that activity happening even in the vacuum, if it wasn't for all of these little fluctuations even in the vacuum, space would not be a coherent thing. It wouldn't be the case that we could have a notion of points in space that are related to each other and where we can expect to move something from one place in space to another. Space would just sort of disintegrate into a bunch of independent points. That activity that is associated with zero-point energy is actually, in our models, basically the same phenomenon as the phenomenon that knits together the structure of space. So, but in any case, in sort of everyday quantum mechanics, there's this phenomenon of zero-point energy, which means that there's always, the molecules never actually get to stand still. They always have a little amount of energy that's associated with the so-called vacuum fluctuations. There are a bunch of different ways to describe it, but it's basically a mathematical feature of quantum mechanics. And that 0-point energy keeps them wiggling around a little bit. It turns out most materials have enough force of attraction between the molecules or the atoms to overcome that little bit of wiggling in the 0-point energy, and so they become solids at absolute zero. The one exception is helium-4, the isotope of helium that has 2 protons, two neutrons in its nucleus. That remains a liquid at absolute zero. And now I'm wondering about helium-3. Does it remain? Helium-3 has very different characteristics, because helium-3, this gets us into a different whole issue, but I talked about this exclusion principle for electrons. That applies to helium-3, but it does not apply to helium-4. I think helium-4 I think it does not apply to helium-3. So helium has this feature that even at absolute zero, the 0-point energy is jiggling around the helium atoms enough that they can't form into solid helium. If you put pressure on the helium, then it will indeed form into a solid. But at standard temperature, at standard pressure, 1 atmosphere, what we normally have, it will not form into a solid even at absolute zero. So, oh boy, okay, I should probably wrap soon here, but there's so many interesting questions here. It's a question from B2 about a chap called Paul Dirac, who talked a lot about constants of nature, and have we come further in explaining constants of nature? Maybe that's a little bit too complicated a question. That there are some things about the world, like the speed of light, Planck's constant, which is the scale that determines quantum phenomena, the gravitational constant, which is the thing that determines the force of gravity. There are these various features of the natural world. Many of those features of the natural world aren't really things that they're things that really define the units of measurement. So I mentioned with the speed of light, the speed of light is really just the thing that converts time units to distance units. And similarly, some of these other things like the gravitational constant more or less converts mass units to other things. So if you think you know what a kilogram is, then you can define what the gravitational constant is. But there are very few most of these things are essentially just definitions of what the units of mass are, what the units of this are, and so on. But there are some combinations of those constants which are dimensionless, that aren't just definitions of sizes of units. Most famous is a thing called the fine structure constant. Has a weird name. It arose originally when people were studying properties of atoms and energy levels of atoms and things, but it's usually written alpha, and it has a value of about 1/137 point something or other. And so that particular constant has been the focus of quite a lot of activity of, can we explain why the fine structure constant has that value? Well, the answer is not yet, but this model of physics that we have should eventually be able to explain that. We're not there yet, and we don't know the extent to which the value of that constant will depend on our kind of structure of the way we describe physics. In fact, what seems to be the case in our models of physics is that there's just one fundamental universe, but there are different forms of description of that universe that give you different physical laws. And so just as I suspect that the fine structure constant, for example, will end up with different values depending on those different forms of description. And those forms of description have to do with saying, well, are we describing the universe in terms of space and time, or are we describing it in terms of some completely other way of representing the different components of the universe? And that will probably determine the values of those constants. And so they're, again, as much a reflection of our way of describing the universe as they are something fundamental truly about the universe itself. But they should be things that are derivable. For example, in our models, And we're not there yet. I don't know how many years it'll be before we are there, but we're definitely on a path that should allow us to be able to explain those things, and at least within the context of our way of describing physics, be able to say, oh yes, the fine structure constant is equal to this combination of pi's and e's and other mathematical constants, or at least something that a computer can compute to a high degree of precision. So that's a thing we hope to be able to do, but existing physics over the last 100 years or so since the fine structure constant was discovered has not really made much progress in explaining the value of it. Okay, maybe one more. Oh, I'm too tempted by another physics question here from Pass, who's asking about the triple point or the critical point. Okay, so I talked about solids, liquids, gases. You think you got a solid, you know what it is. You got a liquid, you know what it is. It pours, it flows. It's hard to squash. You know, a liquid is you can't really compress a liquid too much. And then you have a gas, which you can compress. And you say, well, those are really distinct things, solid, liquid, gas. Well, you can have things, a solid can melt, it can turn into a liquid can boil, it can turn into a gas. There's actually another thing that can happen, which is sublimation, where a solid can turn directly into a gas. That happens with dry ice, solid carbon dioxide, for example, at standard pressure. And so the question is, are these really all distinct, solid, liquid, gas? And it turns out that liquid and gas are not really distinct. So it turns out as you increase pressure and so on, there comes a point at which the molecules are kind of all running around. They're kind of, they're kind of clumped together like in a liquid, but they're kind of also flowing freely like in a gas. And there comes a point where they kind of can't really decide whether they're a liquid or a gas. And the line when you kind of describe in the temperature pressure, these temperature pressure diagrams, so-called phase diagrams, that have these lines that separate things like solid and liquid and so on. And there's a line that separates liquid and gas, and that line, when it's usually drawn, just comes to an end. That's the critical point. That's the point at which you can no longer distinguish between a liquid and a gas. There's a certain amount of clumping in the gas that kind of looks a little bit like pieces of liquid, and in the liquid there's a certain amount of things going freely like in the gas. The critical point is a very interesting place because it's a place where there's a sort of hierarchy of different sized clumps. So there can be a very tiny clump, there can be a very big clump. There's a sort of infinite hierarchy of different sizes of clumps. And so it's a place where if you were to look at this kind of gas or liquid or whatever it is at the critical point, you would see these clumps of all sizes. And so if you look at it sort of through at least conceptually through a microscope, you kind of don't know what the magnification of that microscope is, because at all scales, you will be seeing clumping going on. And so this is a place where actually it becomes mathematically, there's some very nice mathematical features of the critical point, leads to a phenomenon, it's so-called renormalization. It's the use of renormalization in condensed matter physics, which is different from the one in particle physics, although they are connected in various ways. But it's this notion that the scale doesn't matter. It's scale invariant. You can see clumps on all scales. And that allows you to work out a bunch of mathematical features, and the details of the amount of clumping at each size are things called critical exponents. And it turns out that you can work out those critical exponents in a way that's very independent of the details of the materials that you're actually looking at. And that's an important sort of thing in mathematical physics. It's kind of a big discovery of the, I guess 1970s or so in mathematical physics was the ability to do things like that. All right, maybe one last non-physics question here. Let's see. It's a question from Ein. How would you suggest getting a child interested in diving deep into science and technology, not just web programming, but something real? What if the kid's parents aren't very interested themselves? Can the kid be saved, so to speak? for example, my parents weren't particularly interested in science. I got interested in science when I was really young. And I think it's probably even fair to say that I taught myself to read from looking at illustrated science books where they had, captions and, pictures of things and words and so on. So I suspect I was science interested very early for no particularly good reason other than that probably it was not something that parents, teachers, etc. knew about. So I was probably the anti-example of, you need somebody who already knows about something to get you interested in the thing. But I think, the main thing I've observed, I have 4 kids who are terrific, but who don't like me to talk about them. At least some of them don't like me to talk about them in these public settings. Sometime I'm going to have to get at least 1 or 2 of my kids to do one of these, either with me or without me. They would have a lot of interesting things to say. But I would say that my kids have been sort of variously, some of them more interested, some of them less interested in science and technology. I think that my general feeling is that many kids are curious about things, and the question is, what happens to that curiosity? Does somebody kind of help them figure out the answer? Does somebody tell them, oh, the answer is known, but you won't understand it? Or what happens? I think probably the answer is known, but you won't understand it is a pretty guaranteed killer of that kind of interest, or at least for many people it would be. I think the let's go look it up and figure it out, that's probably a good approach. I think that's sort of a good start. I think the thing is that sometimes there's a tremendous tendency on the part of people who sort of know about some area of science or tech or whatever to say to kids, you should be interested in the area that I'm interested in. Well, it depends on the personality of the kid. Some kids will be interested in the exact opposite of the area you're interested in. Some kids will be interested more in the area that you're interested in. And I think that the thing that the thing to realize is, depending on the age of a kid, but the kid is interested in something, even if you don't think it's all that interesting, go explore it, go try and figure it out, go encourage the kid to go figure it out, even if you think, oh, that's kind of a boring thing, because, well, among other things, my observation has been that almost any question will turn out to be interesting if you dive deep enough into it. Even if it seems like, oh, that's kind of obvious, that's, there's nothing interesting there. Or even that question is really hard and you're not going to be able to figure it out. Well, okay, you might not be able to figure it out, but you might be able to figure out some things that are on the edges of that question. And even the process of figuring things out is really interesting. I would say that another thing about science and kids is, for a lot of kids, things in science are just like known by adults and that's all there is to it. Or maybe not known by adults, but it's just like, it's a cut and dried thing. And the process of going from, of figuring it out is not something kids get to see. I mean, kids, will ask their teacher some question about science or something. The teacher will either say, here's the answer, or it's not in the curriculum, or I don't know, or whatever. But the process of figuring it out is very rarely visible. And I think that it is super educational when kids get to see things actually being figured out. I mean, that's easier when it comes to things like mathematical experiments and so on. I mean, I've done many times, I've kind of done live computer experiments with kids and many others, where sort of the surprising thing is that you can go from not understanding something to having had the computer help you understand something in a period of, I don't know, an hour or whatever. And then it's, gosh, we figured something out. It's like, that's kind of the history of science is a history of people figuring stuff out. but the history of science as told after the fact is a story of this was figured out, and so on, just sort of the end of each of those figurings out, of this turned out to be true, this turned out to be true, and so on, not really the inner process of what happened. And so I think that for kids to see things actually being made is super educational. It's educational for everybody. And I think, when it comes to technology, same thing is true. The thing that always surprises people, I think, is that, when you see some piece of software or something, it's just like the thing just is. And the fact that people created it, and there were decisions to be made about how did it work, and there were issues of things that didn't work, and they had to be sorted out, and they had to be resolved, and so on. That process is not usually known or seen by people. And I think when kids or others have seen that process, and particularly have seen the process of going from just an idea to something that really exists in the world, that's a very empowering thing to realize that happens. And I think that's very motivational in terms of getting involved with things like technology or science, if it's a question of figuring things out in science and so on. I think, one thing that can happen in science is there's a lot to know in science. If you go across sort of all areas of science, there's just a lot to know. And I think that, focusing at any given time on the one thing that you happen to be interested in, and not say, oh, I can't discuss that because it's a piece of physics, and to understand that piece of physics, you have to have done high school physics, college physics, graduate school physics, and eventually you'll get to this thing you're actually interested in. That's a mistake, because there's usually a path that goes from fairly elementary things to at least some version of that thing up in the sky that you're interested in, without having to build the whole giant framework of all these different things in the middle. And in a sense, my efforts in these Q&As has to do with finding paths to get to the explanation of something without having to really explain all of the layers that exist. And for example, early in this Q&A, somebody was asking about what size of objects make stars as opposed to planets. And in a sense, that I was realizing that was harder for me to explain than I thought, because I know the official explanations in terms of, equations of state of materials and, various kinds of gravitational instabilities and this and that and the other. But the question is, how much of that stuff can you unpack and not have to talk about and still get to the final result? And that's sometimes challenging. It sometimes requires that one understands the stuff really well. In fact, that's one of the reasons I like doing these Q&As, is because I kind of think I understand stuff like that. And yet when I come to try to explain it in these kind of straight lines without having to go through all these layers of other knowledge, I realize I don't understand it quite as well as I thought I understood it. And it helps me to try to see whether I can make that path and get to, and sort of honestly get to the end without really having to say anything that, saying things which are, if you were to know all of that graduate school physics, you'd say, yeah, that's right. But still not have to know all that graduate school physics to get there. So, well, somebody, Parmenides, is commenting, surely my kids are more likely to embarrass me rather than the other way around. My kids are wonderful, and they would be very, yeah, well, you guys should, particularly one of them, I would love to persuade to do live streams like this. They would be able to talk about some super interesting things, very different from the kinds of things that I talk about. Yeah. Well, okay, I think I should wrap up at this point before I get myself in any more trouble. Yeah, lots of interesting questions. We'll save them up from next time. And well, thanks for joining us. And